Hello students, this is Mr. Allen. Today we are going to look at chapter 5. We're going to get into differential equations and slope fields and things like that. Note I am going to skip section 5 too, which is actually more of a pre-calculus topic. So our objectives today is to use initial conditions to find a particular solution of a differential equation. Use Euler's method to approximate solutions on differential equations. And notice I said here on students, so I'll mention more of that later. And recognize and solve differential equations that can be solved by separation of variables. Again, this is all review material, so this shouldn't be too challenging. There are lots of physical phenomena that can be described using differential equations. A differential equation is simply an equation that's in terms of x and y and some sort of derivative of y in terms of this class. A function y equals f of x is called the solution of a differential equation if the equation is satisfied when y and its derivative is replaced by f of x and its derivatives. So let's look at an example of that. So here we have a second order differential equation right here, y double prime minus y equals 0. And this question is asking us to determine whether the function is a solution for the differential equation. So is y equals 4e to the negative x a solution? Well, in order for us to determine that, we got to figure out what y prime is, or y double prime is. So let's go ahead and do that first. So y prime, well, that's 4e to the negative x times negative 1 by the chain rule, which gives us negative 4e to the negative x. Y double prime is now going to be the derivative of this, so that's going to be negative 4e to the negative x times negative 1, which is 4e to the negative x. Now what we're going to do is we're simply going to substitute this into our original equation. So we've got 4e to the negative x minus, and what was y? Well, y is 4e to the negative x, and we want to know if that's equal to 0. Clearly it is equal to 0. Therefore, we would say that this is a solution for that particular differential equation. Geometrically, the general solution, and by the way, this was a specific or a particular solution for this differential equation. Geometrically, the general solution of a first order differential equation represents a family of curves known as solution curves. One for each value assigned to the arbitrary constant, and keep in mind that constant could be literally any real number, so there's infinitely many of them. So for instance, you can verify a function of y equals c over x is a general solution for x, y prime plus y equals 0. This figure here to the right shows us that the solution of the corresponding differential y over cx, which is the general solution, generates a family of curves, a family of solution curves. So here, for example, when c is equal to negative 1, that's this curve here and this curve here. And then if I pick another value of c, so let's do this one in red. Let's say c is equal to 2. That's this curve here and this curve here. All of these various curves are solutions for the differential equation x y prime plus y equals 0. If I want to know one specific solution, or what we call a particular solution of a differential equation, then an initial condition has to be provided. So let's look at an example of finding the particular solution. So for the differential equation x y prime minus 3y equals 0, verify that y equals cx to the third is a solution, and then find the particular solution determined by the initial, so there's the initial condition of y equals 2 and x equals negative 3. So we've got a differential equation right here. We have its general solution right here. We're asked to find the particular solution, and we're also, we were asked to verify that that general solution works as well. So let's go ahead and do that. So first of all, we know that y equals cx to the third is a solution because when you take the derivative of y, you get 3cx to the second, and then we can substitute that into the original equation. So this is y prime. We already know what y is. We can substitute that into our original equation, which is x y prime minus 3y. So replacing y prime with this and replacing y with this, clearly that's equal to 0. And that's what we wanted it to equal. So that is a solution. The general solution does work. Now let's go and find the particular solution. So we were given that the initial condition is y equals 2 and x equals -3. Here's our general solution. So now what we're going to do is we're going to plug in the -3 for x and the 2 for y into our general solution. That's going to give us, let me clear that off, that's going to give us 2 equals c to the times -3 to the third, and we can solve that for c, and we can see that c in this case is -2/7. Therefore, we can conclude that the particular solution for the differential equation is -2x to the third over 27, whereas the general solution was y equals cx to the third. Try checking this solution by substituting for y and y prime in the original differential equation, which was on the previous slide. Okay, let's talk briefly about slope fields. I'm not actually going to go through and do an example of one, but I do want to talk about it a little bit. Solving a differential equation analytically can be difficult or even impossible, and trust me, I can tell you that's the case. When I've worked my master's program here recently, actually even as an undergrad math student, we had to take a class called DiffEq, which is differential equations. And then in my grad level class, I took a class on advanced differential equations. And in that class, we did not solve hardly any of them analytically. We had to use a different approach. One of those approaches is to use something called a slope field. So consider the differential equation y prime equals capital F of xy, where fxy is some expression in terms of x and y. At each point xy in the xy plane, where f is defined, the differential equation is determined by, it determines the slope, or the derivative, if you will, of that function. So if you draw short line segments, that's what we do when we do a slope field. Oops, sorry about that. That's what we do when we draw a slope field, is we draw short line segments on the graph at select points x, y in the domain. This produces what we call a slope field or a direction field. I never heard it called a direction field, but slope field is what we normally go with. Each line segment has the same slope as the solution curve through that point. A slope field can show the general shape of all the solutions and can be helpful in getting a visual perspective of what the directions of the solutions of a differential equation. So let's just look at an example here, and I've already produced this slope field using technology, but suppose you're asked to create or sketch a slope field for the following differential equation: y prime equals x minus y. So what this is saying is m, the slope of the curve, or dy dx, is equal to x minus y. So if I wanted to find an example, I could use, let's say, the point, I don't know, 1, 2. So what would dy dx of 1, 2 be? Well, dy dx would be 1 minus 2, which is -1. -1. So and here's the slope field. So if I look at the point 1, 2, that's over 1 and up 2, that'd be this point right here. You'll notice that the slope of the tangent line there is -1, which is what we said it was. Similarly, if we picked x and y to be equal, like let's say at 3, 3, which would be right here, you can see that the, is that 3? I'm sorry, that's 3, 2. At 3, 3, which would be right here, not that last guy. at 3, 3, you can see that the slope there would be 0 because 3 minus 3 is 0. So this is the slope field that's generated by this particular differential equation. Okay, Euler's method. I'm actually going to leave this one to you. So we've already talked about Newton's method, and I think I did introduce Euler's method to you last year. Regardless, though, I'm going to leave this up to you. I want you to look online or on the online textbook or Google search a video on Euler's method. And what Euler's method does is it allows you to approximate particular solutions for a differential equation. Now, I'm telling you, I am doing this intentionally. I am not going to show you how to do this. I'd be glad to answer questions on it, but I'm going to leave that up to you, okay? Euler's method. All right, last thing I want to talk about in this video is something called separation of variables. This is section 5.3. Everything I've done up till now is just kind of a general conversation about differential equations. Now we're going to talk about a specific technique that's tested pretty heavily on the AP exam, and that's a differential equation that has to be solved using separation of variables. So if we look at this particular differential equation, you'll notice that it has x term on the left. It has a y term on the left. That's this dy here. And notice on the right-hand side, it's got an x and a y. So if we just try to integrate this the way it is, we've got some problems. Now, you actually can integrate this way with variables of different types on each side, but that's a topic for multivariable calculus, which is what we are not going to discuss today. We're going to try to figure out how to do this without using multivariable calculus, and we're going to do separation of variables. So to begin, note that y equals 0 is a solution. So y equals 0 is a solution. Why would that be? Why would y equals 0 be a solution for this problem? To find other solutions, assume that y does not equal 0 and separate the variables like shown. So all I'm going to do here is I'm going to multiply the dx to the other side, so that puts us in differential form on both sides. So now we got dy on one side and dx on the other, so that's good. But notice I still got y there over on the right. So now what we're going to do is we are literally going to separate the variables now. So this is going to pull the y variable to the left. Now we're in a good position. We have our variables separated. Sorry, let me get my pen going here. We've got our variables separated, which is what we wanted. You'll notice all the x stuff is on the right and all the y stuff is on the left. Now we can go ahead and integrate both sides once you've separated the variables and you've got your differential form set up. So let's see here. What is the integral of dy over y? And the integral of x over x squared plus 4. So what technique are you going to need for this integral? My guess is you probably already know what this answer is. So obviously if we integrate 1 over y, that's just going to be the natural log of y at absolute value. Then on the right-hand side, I would have definitely used some u sub to get 1/2 the natural log of x squared plus 4 plus c1. Now notice I didn't put the plus c on the left. I'm just going to go ahead and write it over here on the right. Now this is a natural log with multiplied by 1/2. So what that means then is I can change that 1/2 into the square root. Notice that that doesn't include the constant c sub 1. Now we could, to get rid of the natural log, we'll just do e to each side. Now I've done a couple of steps here, okay? So the left-hand side should make sense. The right-hand side, you might want to do a couple of the steps to figure out how I got e raised to the c1 and then the square root of x squared plus 4. So it requires you to use some rules with logarithms and exponentials to understand how that happened. Now that absolute value there, we can get rid of that by just putting a plus or minus on the right-hand side. And we can just absorb this. This whole thing right here, e to the c sub 1, that's a constant because e is a constant, it's not a variable. C is a constant. This plus or minus, so we can just change all of that to c sub, just c, just capital C. So this is the general solution to our original differential equation. and we use separation of variables. And that is that. Thank you for your attention. Have a good day.